Okay, so we're going to take a look at mapping notation. And what mapping notation is it's a way to take a coordinate, so one point on like a continuous graph, and find the new point depending on what like the translations and the transformations are, okay? So this is function notation. And the reason we have f inside of where normally the equation is what it means is it can represent any type of function. So we've actually learned quite a few up at this point. You've probably done, that's a terrible Cartesian plane, but you've done linear functions. You've done quadratic. You're currently working on exponential. I don't know if I ever spelled that right. Exponential. You're eventually going to do like periodic, because just periodic, which actually looks like this. And this little mapping notation that we're about to learn, so these two equations here, you can apply them to each of these. Is there any other functions you guys have done yet? I don't think so.
No.
No cubic or anything. Yeah, so it doesn't matter. Technically, even if you use or learn a new function, this notation comes in handy. So what we'll do is normally actually with your linear functions, you really don't use a lot of these letters, but they're actually there. So I'll show you, for instance, with a linear function, what you were used to seeing is something like this. Y is equal to mx plus b, right?
Right.
We can actually expand it to look more like this. Essentially, you can have y is equal to a, and then we'll put the brackets here. Technically, it's k x minus d plus c. Now, you might say, hey, this looks identical to what you wrote up here. And that's because actually this function represents kind of a linear function. Other than we took the f out, it's to the power of 1. This x is technically power of 1. We haven't written anything there, so we assume it's to the power of 1. The only thing is this kind of condenses, and it can condense and be simplified into this form. So that's why we teach it this way, rather than in grade 9 or 8 or whenever you learn it. We don't show all of these. It gets a little too confusing. But technically, all of these can be applied. And what we got to remember is what they do. For instance, A does vertical compressions and stretches. So I'm going to say stretches and compressions. K does horizontal stretches and compressions. D does horizontal transformations or translations. And C does vertical, so up and down translations or transformations, okay? I've kind of showed it there for linear, but what I'll actually do is I'll quickly jump over to this one. It's a little easier to see with a function like this. I've written these letters in. Are those ones we do? A, we usually call this one K actually. D and C, that works, so we'll get rid of this B. Okay, and I'm going to get rid of that. And that. Okay, what I want you to see is the original function here. So we'll move this back to 0. K is 1, A is 1, and C is 0. Oh, that should be 1. Okay, so the blue one's overlapping the red one, okay? We don't have to know too much about these functions just yet. We just know that they overlap each other at the moment, okay? And what that can mean for us, let me see if I can switch that over for a sec. There we go. This function right now, if we write it in function notation, okay, so we have our letters here. Our a value is 1, so it is 1. Technically, this is a sine function, but I'm going to just write f because I know you're not used to sine yet. And then our k value is 1, so our a value is 1. We have an x. Our d value is 0, so we're not subtracting anything. And then outside the function, our c value is also 0, so plus 0. So what this means is this function right now, and anytime we, a and k have to do with really multiplication. This function is they usually call it like the parent function. It's the simplest version of the function. But as we start to manipulate these things, you'll notice things will start to stretch and compress, okay? So as I manipulate the a value vertically, you're going to notice this goes up and down. So you'll notice it goes both ways. And that's why we use the sinusoidal function, because it kind of shows both of them going up and down. Okay, and then it flips at 0. So quadratic functions will do the exact same when I do it to them. Linear functions will do the same. They just look a little different when we do it. I could technically, let's copy this. I don't know if it'll allow me to have two versions of the values. Oh, it might. If I get rid of this. There we go. There's our linear function. When I vertically stretch it in compression, oops. When I vertically do it, you see it just kind of flips around. Essentially, the slope is changing to it. Okay?
Yeah.
We just haven't really talked about it too much with connected to each other. So the A value does our vertical stretches and compressions. A K value does horizontal ones. So on the sinusoidal function, the periodic one, you can really see it looks like an accordion coming in and out. The linear function, it just looks like the slope is changing again. So it's not easy to see in a linear function, but with these more complex ones that you'll get into, you can kind of see how it manipulates them as the numbers change, okay? It's got a cool like visual effect to it. Oh, I missed one. Okay. Those are actually the two hardest to deal with, the stretches and compressions. D is going to horizontally move things left and right. So you'll notice the things moving to the left and to the right here. And it's easy to see that with a linear function. Usually we would see in a linear function, we call that the y-intercept changing. So if you look at it, it's a little difficult to see, but this is like the y-intercept going up, 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 and then coming back down. But really what's happening is it's just shifting along here. Missed 0. And then finally, C does vertical, up and down. Okay, so these four things, these are essentially how our functions can change. Now, how does that help us with our mapping notation? Our mapping notation here, when we get a function and we get a coordinate, so this thing stands for this here, this stands for the new x coordinate. I just put an n there. That just means the new x coordinate. So after we've applied a k and a d, where's the new x coordinate? Same with y. Where's the new y coordinate? Once we've applied the a variable and the c variable, where's the new y point? And the xo just stands for old x coordinate and old y coordinate. So what we can do is I'm going to pull a question out of one of your pages here for exponentials because that's what you're working on at the moment. So let's do a little bit of an exponential function. Let's see if I can find one that's easy.
If it helps, I can give you the ones he assigned. Or actually, it's okay. It's better if you find your own.
Yeah? Okay. I'm going to grab one here. I see one. We have this exponential function. They called it h at x. So this is number 2c. Okay? Just so you have reference to it. Is equal to 7 x minus 4, so the exponent is x minus 4, and then minus 1. So the first thing we have to do is kind of piece this together. We didn't quite do it yet, but we should do this. We should find the general equation for an exponential. So the general equation for an exponential looks like this. A, B, it's kind of outside of our stuff, but it deals with the base of the exponent, okay?
Yeah.
Then we have K would be up here. I'm going to put that also in blue because that's what we normally put it. And then we have x minus d. Okay. And then plus c, I believe, was the outside one. Okay. So if you remember in our function notation, I'll quickly try to put it up here. Our function notation, we had a at f, k, x minus d plus c. Okay. That new thing b there, that just stands for the base because exponential functions can have different bases, right? A very common one is to see like x to the power of 2. In the one above, do you happen to know what the base is in this question here? What would be the value of the base?
Would the base be 0.5?
Yeah, great. So it'll be a little easier to look at now that we know a value for the base because this one has to represent a general equation. But now that we have an actual base, we can write it in for this specific question. And it'll help us with our translations and stuff. So our base is 0.5. So think of it like a is being multiplied by that, okay? Our exponent up here, we have a k, we have an x minus d. Close the brackets out here. So I added an extra set of brackets just to make multiplication look a little easier. And then here. So the next thing we're going to do is let's just figure out what our a value is. What would be our a value in this case looking at this equation h at x?
7?
Yeah, excellent. What about c?
-1.
Mm-hmm. What about d?
-1. -4.
Yep. And then this one's hard. What's k in this one?
Would it just be the x?
Close. What coefficient is in front of x, would you say? If there's nothing there, do you know what we assume? What value we assume?
1.
Yeah. So because there's nothing there, we actually just assume the k value is 1 in this case. Okay, they don't write it in because it's redundant, but we're going to assume that's the case. What's great now is we've just outlined our a, k, d, and c, which means we can now try to use this little function notation. So our new x value is equal to the old x value divided by k, which is really nice in ours because that's simple, plus, minus d. And our new y value is a multiplied by the old y value plus c. Okay, so we can actually write this equation out now because we have values for it. So the new x value is equal to the old x value divided by 1, because that was our k. And our d was 4, so it's going to be minus the value of 4. Okay, and then in our new y value is equal to the a value was 7, so 7 multiplied by the old y value plus -1, so we'll just write subtract 1. So we have this function notation. So what I'm going to do is I'm going to go to a graphing calculator and I'm going to show how this function notation will get every single point for us. So let me jump back over to our graphing calculator. We can take a picture of this page. Great. And then we'll close it. And then let's do a new graph. Great. So let's do a new graph here. I'm going to do a exponential function of base 0.5. Okay, so that's what an exponential function of 0.5 just normally looks like, okay? And if I can, I should be able to make it into a table. There we go. There we go. This table is going to help us a lot. We're going to make a couple tables. I'm going to put the new function in. So the new function we had was 7 multiplied by 0.5 to the power of x minus 4. Whoops. Should still be up there. Minus 4. What's going on there? I'll put in brackets, I think. There we go. X minus 4 minus 1. So here's our new function. Okay, kind of difficult to tell where the heck it was supposed to be. We're not 100% sure. But I'm going to do the same as this. I'm going to turn this into a table also. There's a reason I'm going to do that. It's going to help out a little. Is our little equation, okay, you notice we have our values here, -2 and 4. We're going to, actually this new equation is actually going to change it a little, but I'm going to find out where the new point is. So I'm going to write the two equations we had for mapping notation. We're going to write them out here just so we have a reference. So the first one was the new x value is the old x value. It was technically divided by 1, okay, which isn't going to change anything, -4. And the new y value is equal to a times the old y value minus 1. So how do we find this coordinate, let's say? This coordinate here happens to be -2 for x, okay? We're going to use this equation to find out where it is along this line, okay? It takes a while to draw it this way because we're going point by point, but what's neat about it is we'll get a very accurate answer. So we're going to plug -2 into this equation. So I'll kind of do it on the side here. The new x value is going to be equal to -2. So we replace the old x value with -2 divided by 1 minus 4. Really what this is going to be is -2 divide 1 is just -2. And -2 subtract 4 will be -6. So this x value is actually way back at -6. So it's taken a big, somewhere back here. So we'll have to go back and find it. I'll plug it into this table to find out where it is after. And we'll also look into where's the associated y value with that. So we'll plug in the y value here. Well, the new y value is 7 times the old y value The old y value in this case was the number 4. That's where we're getting this one here. So think of it like we've taken this coordinate and we're plugging each point into these equations, and then subtract 1. Well, 7 times 4 is 28. Subtract 1 is 27. So how we can check this, so I'm going to go into this little equation here. And the x value we said was -6 is the new x value. Oh my gosh, this thing took right off. Why did it take right off on us? 7 times. Does it have a dot for times? There we go. There we go. There we go. Let's take a look at this. Put our values here. Oops. Caught the error. This equation here, which means I wrote it wrong on the other one, should have been +4. +4 changes this to become -2, and which means I wouldn't need this part. Sorry, not -2, +2. And the y value being +27, and there we go. We have an x value of 2 and a y value of 27. So we found the new coordinate. This new coordinate is actually somewhere up there. If I can zoom out a little, maybe. Let's see if they'll let me zoom. If I zoom out, I think it's going to change everything on me, but yeah, change a little. But there it is. There's that coordinate we were looking at. So this coordinate here translates up there. So what we can do is we can go about that in every single one of these points. We can plug -1 into this equation and 2 into this equation, and it'll give us the new point. So we'll do that again just so we get the hang of it, and then we'll just kind of generalize the rest. So the next coordinate is -1. So this formula should say plus. The new x value is the old x value, which in this case is -1, divided by 1 plus 4. This becomes -1 plus 4, so it should be 3. So our x coordinate should be 3. And our y coordinate, the new y coordinate, is equal to a, which was 7, times the old y value, which is 2, minus 1. That becomes 14 minus 1, which is 13. So it should be 3 and 13. The next one, we'll plug it in. Sorry, this page got a little messy, but let's get rid of this one.
Why would you make it +4 instead of -4?
Oh, that's just because, I'll jump back to the other page. Good question. When we pulled it from here, its value was -4.
Right.
And this is a subtraction sign. So what should have happened when I grabbed it, let me get the, sorry, I have to switch pages when I'm writing. Here we go. I should have put in minus -4, which should have came out as +4 in this case. I just forgot to bring down the negative here. So see how that's x minus 4? That means our d value is -4 there. So when I bring it down here, it should have been minus -4, which essentially turns into +4. Does that make sense?
Okay.
Yeah?
Yeah, and if it was just 4, it would stay negative?
Yeah, I would have just said it would have been -4 in that case.
Okay.
Okay, where's that graphing calculator? So this is a way that you can find all the points when going through it. This is really one point at a time. So the downside of this is if you have 5 major points, you're putting, what's going on here? There we go. You're going 1 point at a time, so it's a bit slow. So the next thing you want to do is figuring out how to do this quicker with exponential functions. So that'll be the next thing we'll talk about here.